Hi everyone, I'm going to show you how to get the magnitude of the response when doing the modal analysis in Abaqus. Basically in FRF, when you take the result, it will show you just the real part of the response, so you will see entire resonance. In order to have the peak, just the peak in the response, you have to force Abaqus to show you the magnitude of the response, which comes from both imaginary and real part of the response, not just the real one. And to the start, let's just do, create a simple cantilever beam. Let's just take it 3D solid now. And just add something. And I think it's good for now. I don't want to be very specific with anything. And yes, we prefer a very narrow, thin, and long beam, so the amount of vibration will be very low. And before going to the material module, let's actually modify this model here. We need to add addition to this model. We will use the points later on there, obviously other ways as well. You can add reference points. I mean, it's totally up to you. There is no strict regulation. A very simple material. It's basically steel. Um, just let me tell you that first you have to run this frequency analysis before doing the steady state dynamic. I mean, it's not even shown here. You have just this option, which is direct. You know, maybe we will need the model one. So the model will appear after doing this frequency analysis. And we want the first 5 natural frequencies. I mean, it's totally up to you. You can have 10, the first 10, or whatever you want. And let's define the boundary condition. We want a very clamped beam, so let's close every movement at the end of the beam. Let's do the meshing. Let's check. That's a bit big for elements. It's small. Let's just. No, that's good. And mesh. Yeah, this job is a bit. Okay, let's check the result. First natural frequency is 14, roughly 14 hertz. The mode shape is vertical direction. Let's just make it a bit slower. You can see the direction of movement. Just try to memorize this mode shape and direction of movement because we will need it in just a few moments. And then the second mode is this with the frequency of 8p, and the third mode, the fourth mode, and the fifth mode, which is torsional. Let's just bear in mind that the fifth mode frequency is 254.89. Let's just round this up to 260, 270. And now we need to add the next step, which will be steady state dynamic model. With, as you can see now, it wasn't visible just moments ago. And the lower frequency will select 0, the higher, as I just told you, let's stick to 270. For the damping, we can use a structural damping. The first mode is 1, the end mode is 5, and constant, let's just stick to 2%. We also need a field output. We need translations and rotations, mostly translations. Now we need to add the load to the beam tip. Here, as you can remember, I just showed you the first mode. The mode shape was like this, and like this was in Y direction, so we prefer to have a load in this direction. So the chances of the first mode being activated is quite very much. And let's select this point. I also change the name of the set to, let's modify, not change it, loading point. As I just told you, we need the loading to be in Y direction, because this way the chances of first mode being activated is quite very high. And if we change the direction of load, for example, in X direction or in Z, other modes are more likely to be activated, and we don't get the response that we want. Let's just put it downward, use minus. Let's just stick to 5 newton for now. Check the mesh, which is fine. Let's run the job again. Okay, let's check the results. As you can see, the frequency is now 270. This is the last of the range that you defined. Let's extract the FRF from this analysis. We stick to U2 for now because it's in the direction of Y. And well, obviously the first mode is activated and everything is in this direction now. And for the point to study, let's select the loading point we just defined, and let's uncheck the first step because there is no field output modified for the first step. Everything is in the second step. And this is it. As you can see, the FRF output shown here, it is showing anti-resonance, and the response is the real part of the response. It's not the whole response. I mean, it's not the magnitude. It's just the real part. In order to show the magnitude, so you can see just a peak, not a valley and then a peak. This is anti-resonance. And let's use this option here, complex form and magnitude. We need to get the result again. I mean, you don't need to run the simulation again, but just to ask Abaqus to give you the result. Everything looks fine. And here it is. You can see the peak. There is no anti-resonance here. And just to uh, uh, visual insight about the amount of, as you can see, it's 1473, which is the first natural frequency, and we can make sure that the first mode is activated here by this loading. Thank you very much for watching this video.